For our second lecture, we're going to be taking a look backwards at some topics from algebra that are going to be necessary for some of the later work that we're going to do in this module. Specifically, we're going back to the prerequisites chapter, section 5, to take a brief look at functions. We want to make sure that we're familiar with the language of functions, as we're going to need it when we start talking about trigonometric functions. For this particular section, we have a handful of goals. First, we're going to look at a broader class of idea known as relations. We're going to go ahead and investigate what it takes for a relation to be a function, and we're also going to look at the function notation that we're familiar with. In addition, we're going to focus a little bit on finding domains of functions as it's relevant to our work here in this class. We're also going to use functions to briefly model and solve real-life problems. I say briefly because we'll actually be using this as little pieces throughout the semester. We're going to continually come back to this idea of using different functions to model real-life situations. The last thing that we'll do today is look at what's known as a difference quotient. This is an idea that hopefully you saw in your previous coursework in algebra, but if you haven't seen, you're definitely going to want to see it now, as it's vital to understanding the later parts, or rather, the early parts of calculus. If you don't understand a difference quotient, you're not really going to be able to get off the ground. To kick things off, we're going to start with our introduction to functions and function notation. So I mentioned that there is a broader class of idea, something that exists above functions. The idea here is what's known as a relation. You can read for yourself, but the idea is that any correspondence between two quantities is what we call in mathematics a relation. There are various fields of study that focus just on relations themselves. Here is an example of something that would be classified as a relation that may or may not be a function. Let's say, for example, that I have a triangle who has a couple different points somewhere on my coordinate plane. And I'm going to go ahead and translate it by moving it 5 units to the right and 3 units up. In this example, the points on the original triangle are going to be in a correspondence with the points on the later triangle after this translation. That is a relation. I can take these two quantities, the collection of points for the first triangle and the collection of the points for the second, and tie them together 1 to 1. That is a correspondence. It doesn't necessarily have to be 1 to 1. Any tying of two quantities is what we call a relation. Now, we see relations all over the place. When we're dealing with things like equations and formulas, these are some low-level examples of relations. The example they give here is kind of an interesting one. The simple interest earned on $1,000 for 1 year is related to the annual interest rate by the formula I equals 1,000 times R. So this is actually kind of interesting because it also talks about direct correspondence or correlation here. In this particular case, the amount of interest we earn is going to be directly proportional to whatever the interest rate is. A higher interest rate will mean more interest, and the opposite is true as well. Now, what's interesting about this particular formula is that when we're looking at it, the thing that is probably going to be in our control to vary is going to be this interest rate R. That's controlled upon the account that we choose to put this money into. So we're going to look at, if I change R, how does my interest rate change in response? This kind of back and forth between an independent variable R and a dependent variable I is what takes this one step further. This is where we start to enter the relation, or rather the realm of functions. In this particular case, the formula that we saw in the previous slide is a special type of relation because each item from one set corresponds with exactly one item from the other set. In other words, there is a specific interest amount that corresponds with a specific interest rate, and there's no mix-up between different portions. For every interest rate, there is exactly one interest amount, and vice versa. Whenever we see something like this, we say that this relation is a function. Now, specifically, we're saying that for each input, there is exactly one output. The exact definition is given here in the box. There are a couple things that I want to highlight, and that again is specifically the direction here. A function f from a set A to a set B, so we're going with an implied direction, A to B, is a relation that assigns to each element x in the set A, so we're starting with elements in whatever A is. It can contain one thing, it can contain infinitely many things, but we're taking for each item, we're going to tie it to exactly one element in element y in set B. Now, the key part that I really want to focus on here is the phrasing exactly one. Normally we say this with, maybe only one or at most one. We need to be very careful here. When we talk about a function, we say exactly one. The important part of that is saying, yes, we can't have more than one element y that we're assigning an x to, but it's also saying that x has to go somewhere. It has to be assigned to something. We can't have an element x in set A that doesn't have an element y in set B. So that's another important part for us. The set A is what we call the domain, or set of inputs, and B is what's called the range, or set of outputs. There are some other associated ideas, such as codomain, which is a slightly different name for set B, but there are some restrictions on what it does and does not contain that we really can't get into for right now. The bigger thing that I want to tie together is that the domain for a given function is the set of all inputs that have exactly one element in our range. We'll talk about this a little bit later when we talk about restrictions on the domain of certain functions. Here are a couple examples that we're going to take a look at, just talking about when a relation becomes a function. So in this particular case, we're looking at a function as a discrete function and a set of ordered pairs. I say discrete because in this case we have non-continuous domain. We have just 6 points that comprise our actual function. The other piece that I want to talk about is that this is given to us as ordered pairs. Whenever we receive ordered pairs as a function, the first coordinate always indicates the input, and the second coordinate always indicates the output. Here they say x value and y value, but in later parts of mathematics you might see these represented using different letters. One of the key things here is that the first coordinate always goes with the letter that alphabetically comes first. So just a little bit of a side note for the future. In this particular case, we see that each input has exactly one output. 1 goes to 9, 2 goes to 13, and so on. You might note here that both 3 and 4 go to the same number, but that's all right. The only idea here is that no input, no x value, can have more than one y value associated with it. You can see a few more different pieces here laid out. We have each element in A must be matched with an element in B. This is what I was talking about before. It's not acceptable to have no place to go. X has to have a specific output that it corresponds with. Now, some elements in B may not be matched with any element in A. This is something that I was talking about a little bit before with the idea of codomain. A codomain is the set of all possible outputs for a function. The range is actually the set of all actual outputs, the things that we actually map to. So that's the distinction that I was alluding to previously. This is what I was just talking about above with 3 and 4. 2 or more elements in A may be matched with the same element in B. They can do that, and it's still perfectly fine to call it a function. The only key thing that we can't have, an element in A cannot be matched with 2 different elements in our set B. So this is a brief summary of the ideas that hopefully you've already seen and talked about.